Hello everyone, welcome to Ee477. So this is your TA Hong Yufu. So today I'm going to have a videotaped discussion on the sample midterm we had on last year, actually spring 19th. So I'm gonna go through all the problems, and in case you have any like confused part about the solution on the website. So first, let's see the problem one. So problem one is very similar to the homework problem we have. So this is in this case it's for a NMOS aluminum gate oxide silicon oxide dielectric transistor. So we're gonna calculate its VT0. So the VT0, as we all know, it's VM as minus 2 phi f sub minus QB O COX minus QI over COX. So when you're having a real midterm, you probably just wrote this on your cheat sheet, and you can bring into your answer sheet. So we know so then we can recursively calculate all these terms like what we did in the midterm. For example, VMS equals phi ms minus QOX over COX, and in which QOX is Q times NOX, which is given, and the COX is epsilon OX over TOX. And for the phi ms, it equals phi m minus phi s. So phi m is for the aluminum gate, and phi s equals to chi plus Eg over 2Q, then minus phi f sub. So for the NMOS, phi f sub equals KT over Q line Ni over Na. So remember, this is for NMOS, in which in the substrates, those are acceptors. And then we know the QBOX, it's just minus 2Q Na epsilon Si times 2 times phi f sub. And Qi is Q times Ni, which is given. So with all this, so then the final step is just to plug in those numbers. And if you prepared well, you can just write all this down on your cheat sheet, and you're ready for this kind of questions in the midterm. All right. So I think this is pretty much about the homework one, the problem one of the sample midterm. So for problem two, which is this stick diagram with the VDD and PMOS for input, and the diode connected NMOS, correct? VL is here. So you are asked to calculate the VOL and VOH add out. So if you look at the hint, we already know that when we can calculate the situations when the V in is low, which means VOL, which is low, and V out equals VOH, which is high. So in this first situation, we can count. And the second situation is when V in is VOH, which is high, and V out is VOL, which is low. So for the first case, we know now V, we can see for the PMOS, the input is low, and if we calculate the VGSP minus VTP, so for here I'm using the absolute value. It's this is a VDD minus VOL, and VDSP is VDD minus VOH. So this is bigger than this, so which means the PMOS is in linear region. So remember, this is a absolute value. So PMOS is in a linear region. And for this diode connected NMOS, it's always in the saturation region. So we can, and this is for situation 1. Then we can list the KCL on this node, so that we know the relationship between the VOL and the VOH in case 1. So remember, PMOS in the linear, so just write down 2kp prime. So prime here means let me write it here. Kp prime equals mu p cox. Kn prime equals mu n cox. So 2 kpm W over LP times 2 VGSP minus VTP times VDSP minus VDSP square. So this equals to the NMOS part, which is 2kn squared W over n times VGSN minus VTN squared. So for this we know that, so VGSP here means VGP minus VSP. So VGP minus VSP is VOL minus VDD. So this will become so VGSP minus VTP will become VOL minus 1.6, and VDSP will also become VD. This become VDD minus Vout, which is VDSP, which is Vout minus VDD. So here it's Vout, which is a VOH minus VDD square. And for the PMOS, for the NMOS, VGSN equals to VOH. So it's a VOH minus 0.4 for this. So it's okay. So let's write it down again. VGSN minus VTN equals VOH minus 0.4. So we can plug in, plug back, and this is page 1. Let's go to page 2. So page 2. So we can have this equation. The first critical equation we have for this problem is 4 VOL minus 1.6 times VOH minus 2 times VOH minus 2 square equals VOH minus 0.4 square. This is for the situation 1. This is page 2. For situation 1, we have here. Then for the situation 2, and for the case 2, which means PMOS is in saturation because VDS equals let's say the VDS absolute value equals VDD minus VOL, and the VGSP minus VTP with absolute value is VDD minus VOH. This is bigger than, of course, VDS is bigger than this, so it's in the saturation region. So in this case, we write down the 2Kp prime W over LP times VGSP minus VTP square equals 2 over Kn square over 2 W over L and VOL times VTH n square. So then we plug in the number. We know that it's 2 times minus 1.6 plus VOH square equals VOL minus 0.4 square. So this is equation 2. So by giving initial VOH as an input, so we can alternate from equation 1 and 2. Then we know VOH equals 1.6. Then we go to equation 2. We know the VOL equals 0.4. Then we go to equation 1. Then we know VOH equals 1.62. Then we go to equation 2 again. We know that VOL equals 0.37. Then go to 1 again. We know VOH equals 1.26. So this is pretty much what is asked on the question. If you can reach these steps, you're fine. You can get all the full scores of this question. But there's also a bonus question, is because that actually in the real case, if you see the schematic of this problem, when the V in is high, the V out can reach just below the VTN, which is NMOS, the threshold of NMOS. Then the NMOS will shut down. So in the real case is that the VOL will be slightly smaller than 0.4. Then we can have the VOH calculated in this case, which is 1.4 volt. So if you can see that those won't be happening in the real case, because VOL can never reach to this number before the NMOS shuts down, and before the both P and NMOS shut down, and you can see that actually the VOL is this, and the VOH can be calculated this. You can get a bonus point. So I think this is pretty much about the problem 2 of the sample midterm. Now we can switch to another page 3. So then we can start talking about problem 3. So for problem 3, if you read the problem, it's about the physical scaling, and you need to calculate the delay and the on-off ratio that is influenced by the by this scaling. So scaling of the transistor looks like this. So if you imagine this is a cross view of the transistor, for example, it's an NMOS. Just a quick example that this is the length and width of the channel. So, and this can be a gate. So, what is called by the horizontal dimension is this dimension. This direction is a horizontal direction, which means W and L, and this direction is a vertical direction, considering the TOX here, and also the voltages are also scaled. So by M, so we know that the on the horizontal direction, W and L are scaled by X, and on the vertical direction, TOX is scaled by Y, and on the voltages, VDD and VGS are scaled by M. So with all this scaling considering into consideration, we can start calculating the new delay. So we know the gate delay of this schematic with three inverters as load. So this is R times R is the resistor, is the equivalent resistance in this inverter. Can be R here. We can assume it's same, and actually the load here is one diffusion plus 3 gate. We can assume it's like this, and by this scaling, we know that the capacitance, we can call it C nu, is actually W times L, we call it top W prime times L prime times COX prime, which is W over X times L over X times epsilon OX over TOX over Y, which means it's Y over X squared C old. Okay. Then for the on current, when it's in we say it's in saturation region, it's COX W over L VGS minus VT square, and we plug in all this scaling. We know that it's epsilon X over TOX over Y, W over X and L over X, and VGS minus VT square over M square. And this is we can see it's Y over M square I odd. So then we know the delay. The delay is we call this gate delay prime equals to VDD over I on times the C nu, which is VDD over M times Y over M square I odd times this is this is C new is y over x squared C old. So which means the new gate delay is m over x squared gate delay old. So this is a final answer we have for the influence of the scaling on the delay. Alright, so then if we look at the on-off ratio, we already have I on prime equals here y over m squared I old. So the I off is I sub prime, it equals to W over L, W prime over L prime mu times COX prime and minus 1 theta t squared e minus e to the minus vt over and theta t. So we can see the only influence is here and here. So we know that it's equals to y times e to the 1 over m I sub old. So we know the on-off ratio will be the new ratio will be I on prime over I off prime equals y m squared over y e to the 1 over m. So it equals to m squared e to the 1 over m of the old ratio. So this is a final answer we got for the problem 3 of the sample midterm. So I think this problem is pretty straightforward if you know that all the scalings are done in this way, that you just need to plug. So then you know the expressions of all this, and then you plug into the expression, you can get the final answer. Okay. So this concludes problem 3 of the sample midterm. Now we can go to problem 4. So for problem 4, we have a schematic like this. With the PMOS part is B, A, D, C, and A, B, C, D. On the NMOS part. So this is output X. And we know that the beta ratio is 3, so the ratio of P and N should be 3 to 1, generally speaking. Then it's asked that we want to design in the logic gate such that the worst case propagation delays are from the high to low and low to high are both equal to that of a minimum size CMOS inverter. So the minimum size inverter will always be, in this case, will be on the NMOS side. And of course, this branch has got 2, and this only got 1. So this is the minimum size the CMOS inverter, CMOS, which is this NMOS. So we can set this ratio as 1. Then we know So for the worst case, we want it to match to 3 to 1. So this to both of this will be 3 to 1. So this is 1. So this is equivalent to this. So both of B and C has to be 2, and both of B and D has to be 2. So this is a 1 here. And for the 3, this is a worst case. So if it's a 3, we need to put 9 on all the 3 of A, C, D. Then B is in parallel with DC, so we know that B is 4.5. So I think this is a pretty straightforward for part A of the problem. Then so this is part A. A is already everything here on the ratio here. So for point B, we know that A, B, C, D is changing from 1, 0, 1, 0, 0 to 0, 1, 0, 1. So D is changing. D is from off to on in this case, and X is falling. So so the output will be discharging from BD, and we all know so we know from the part A that B and D they have a ratio of 2, so we know that the RE equivalent is just R, and so the equivalent W over L is just 1. Then we just need to calculate the tau PHL, which is by definition CL times VDD minus V 50% over I average. So we've already know C load and the VDD minus V 50%. So we know that we just need to calculate I average. So in this case, I average will be the average of when VDD is V in is VDD and V out is VDD, and when V in is VDD, V out is 50%, V 50%. So we know that, start a new page 5. So we know that when the V in is VDD, V in equals V out equals a VDD, this nMOS on D will be in the saturation region, absolutely. And when the V in equals a VDD, and which is a 1.8 in this case, and V out equals V 50%, it's 0.9. Then in this case, VGS minus VTH equals 1.35. It's bigger than that. So in case 2, it's in linear region. It's in linear region. So based on this, we can calculate the equation we got here for case 1 and case 2, and average them by sum of 1 over 2. So in case 1, it's case 1 is I equals to half of Kn square W over L equivalent VDD minus VTN square. And in case 2, I equals VDD minus VTN, which is VGS minus VTN. The VDS is half VDD. d square. So then just plug in those numbers and go back to this equation. Then we have I average checked. So by this we can have our final result of tau p high to low. So this is how it's pretty much self-explained in the solution. So I just explain again on the step by step on the problem 4 here. Okay, so this concludes problem 4 of the sample midterm. Then finally we are here at problem 5 of the sample midterm. So this problem is very much like what we had in the homework 3, problem 2. All right. So we're calculating the delay from here to here. So then we need to have the Elmore delay model here. This is we can call this RPRN, so they are all equal to same. Oh, sorry for this. Then here's a diffusion capacitance. Then it's what's important is the wire. It has to be, so for this part it's a RC model, but for the long wire we need to make it a pi model. So we split the CW to half. Then here are, so this is this is a 4 times, and this is a 16 times. So we have a 4 CG here at the end. This is for part 1. Then there is another delay on part 2, which is so this is 4 times, so it's R over 4 here, RP over 4 and RN over 4, and but here the diffusion will be 4CD. Then similarly we need to use a pi model here. And remember this is a 16 times, so we have a 16 CG here. So we just need to add from the Elmore delay from here to here for part 1, here to here for part 2. Okay, so for part 1 it will be RP times CD plus this is 3D over CW and plus 4CG, then plus from here the second resistor times this half of this and 4CG. So similarly we can get this. So if you have this model correct, and you have all the sizings correct, and you have the Elmore delay calculation correct, then you can have all the scores for this problem 5. So I think this is pretty much about the this discussion of the sample midterm. So I wish you prepare well for your midterm, especially cheat sheet, and good luck. Thank you, everybody. Goodbye.